In this video, we will discuss the concept of local maximums and minimums and how we can use properties of the first or second derivative to classify them. So if S is a domain of a function f and c is in that domain, we say that f of c is a local maximum value if f of c is larger than f of x for x near c. So what does that really mean? Well, let me go ahead and draw a function on kind of the domain listed here, going from one point to another. So just kind of an arbitrary function I could draw would be something that looks like this. So say y equals f of x. And if we kind of focus in on this point, let's go ahead and call it C1, we notice that if we really look in just that interval around C1, so when I'm close to C1, we see that the function outputs are largest at C1 itself. So in this case, we would say f of C1 is a local max. It's bigger than everything immediately around it, but of course it's not the absolute max or the maximum value, which is going to occur in this case at that left endpoint. Likewise, f of c is a local minimum if it is smaller than everything near it. So if I look at this point C2, we would note if we stay close to C2, C2 is where that smallest value is attained. So we would call f of C2 a local minimum. Of course, it's not the actual minimum value in terms of the absolute minimum. That occurs down here. But it's a local max, a local min, and these are points we are going to be interested in finding. Now, a simple observation in terms of the derivative shows us maybe exactly how we can classify a critical point of a function as being a local max, a local min, or neither. So when that first derivative is 0, there's really these three possibilities. And notice in the graph up here that each possibility is indicated. If the derivative is positive to the left, i.e. your function is increasing, and then increasing to the right of a critical point, then you will not have a local max or local min. Likewise, if it's decreasing and then decreasing. So if f prime does not change sign at a critical point, it will be neither a local max or local min. But if you're at a local maximum, say in the second picture, notice that the derivative is changing. You're going from increasing to decreasing, i.e. positive to negative derivative. So positive to negative will give you a local maximum. So if f prime changes from positive to negative, then you have a local maximum at C. Likewise, if you have a critical point, say in this third picture, where you are going from decreasing to increasing, you will have a local minimum. So if f prime changes from negative to positive at C, then f has a local minimum at C. So let's go ahead and see how we can use this in a specific example. Oh, before using this in a specific example, let's discuss the second derivative test as well. So if we have a critical point, we can also use the second derivative to classify it. And two simple pictures really illustrate this. So if we have a function that looks something like this, and we have a critical point at C, and note we know this is a critical point because the tangent line is horizontal. So in this case, we would say that f double prime of C is positive because the function is concave up. And notice that concave up at a critical point corresponds to a local minimum. So positive second derivative implies C a local minimum. And this is at a critical point C. Similarly, if we draw kind of the opposite situation, and we look at our critical point, so our critical point C, where that tangent line is horizontal. In this case, the function is concave down, so the second derivative is negative, and a concave down function at a critical point is going to have a local maximum. So negative second derivative at a critical point implies that that critical point C is a local maximum. So for the function given here, let's go ahead and find the critical points and then use either the first or second derivative test to classify. And for this first example, we'll actually go through and use both the derivative tests to classify. So the first thing we need to do is find the critical points. So differentiating our function, f prime x is equal to x squared minus 2x minus 3. To find the critical points, I set it equal to 0 and I solve. And the quadratic we have is something that factors nicely. This would be x minus 3 times x plus 1. So we have two critical points. Our critical points are x equals minus 1 and x equals 3. And what we would like to do is classify each of these critical points as being either a local maximum or a local minimum or neither. So let's go ahead and make a number line. So we have a critical point at minus 1, 3. What we need to do is check the sign of f prime on each of these intervals and see how that sign is changing at a critical point. So let's check a few test points. So x equals minus 2 would be a test point in that leftmost interval. Plugging that into f prime, we would have minus 2 minus 3 times minus 2 plus 1. And that would be a negative times a negative, which is a positive. So f prime is positive to the left of minus 1. If we plug in x equals 0 to f prime, we would have 0 minus 3 times 0 plus 1, which is a negative times a positive, so negative. If x is equal to, let's say, 4, and we plug in 4 minus 3 times 4 plus 1 is a positive times a positive, so a positive. And now we can see exactly what's going on at each of our critical points. So if we look at minus 1, and how I remember this is I draw above. Our function is going from increasing to decreasing. And if you're going from increasing to decreasing, x equals minus 1 will be a local maximum. So x equals minus 1 is a local maximum because the derivative changes from positive to negative at x equals minus 1. And as long as you draw what's going on above your number line, we could just say x equals minus 1 is a local max by the first derivative test. For the second critical point 3, we see that we go from decreasing to increasing at our critical point. So x equals 3 is a local minimum, and we'll just say by the first derivative test. And oftentimes we will just abbreviate f dt for the first derivative test, s dt for the second derivative test. So let's go ahead and apply the second derivative test to this function in these critical points as well. So we have all of the information from the previous slide. If I want to apply the second derivative test, I need the second derivative. So f double prime x is equal to 2x minus 2. And I need to check each of my critical points individually. So if I'm at the critical point x equals minus 1, we have f double prime of minus 1 is equal to minus 4, which is less than 0. So remember, if you have a negative second derivative, that means concave down. So we're thinking concave down, that corresponds to a local maximum. So by the second derivative test, x equals minus 1 is a local maximum. And now we check our second critical point of 3. If x is equal to 3, f double prime of 3, this value of the second derivative, is going to be 6 minus 2, which is 4, which is positive. So positive second derivative means concave up, which corresponds to a local minimum. So by the second derivative test, x equals 3 is a local minimum. So let's look at another example. For the given function, in this case x to the fourth minus 2x squared plus 3, let's find and classify the critical points. So to find the critical points, we differentiate 4x cubed minus 4x. We now set this equal to 0, and we solve for x. So each term has a 4x in common. When you pull that out, you're left with an x squared minus 1. So x is equal to 0, or x is equal to plus or minus 1. So we have 3 critical points, and we need to classify these. And thinking back to our previous example when dealing with this polynomial type function, applying the second derivative test turned out to be a bit easier because we don't have to make a number line and think about where something is positive, where is it negative. We can simply evaluate the second derivative at these 3 points. So f double prime of x, just differentiating term by term, is 12x squared minus 4. So now we need to go ahead and evaluate at each of these critical points. So we have f double prime of 0 is minus 4, which is less than 0. So by the second derivative test, we're going to classify each of these. X equals 0, so we think negative second derivative is concave down. Concave down is going to be a local max. And as silly as it seems, every time I go through one of these problems, I always draw this generic, say, concave down, so I see local max. And it really helps make sure that I don't make a silly mistake. So f double prime of, well, either plus or minus 1 is going to be 8, which is positive. Concave up corresponds to a local minimum. So x equals plus or minus 1 will be local minimums. So by the second derivative test, we have classified the 3 critical points of our function.